Dear friends, welcome in the class of mathematics. In last lecture, we have seen rule second for finding integrating factor and example on it. Today, we have to see rule third and rule 4 for finding integrating factor and examples on them. So let us start. Third rule for finding integrating factor. If 1 upon n dA by m by dA by y minus dA by n by dA by x is a function of x alone, say f of x, then e raised to integration fx dx is an integrating factor of the differential equation 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0. This is the rule. This rule says if 1 upon n dA by m by dA by y minus dA by n by dA by x is function of x alone, that is fx, then integrating factor of the differential equation 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0 is given by e raised to integration fx dx. Now we have to see the proof. Given differential equation is 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0. Denote this differential equation as equation 1. To show e raised to integration fx dx is an integrating factor, so multiply e raised to integration fx dx with the given differential equation on both sides. We get m into e raised to integration fx dx into dx plus n into e raised to integration fx dx into dy equal to 0. Denote this is equation number 2. This is of the type m dash dx plus n dash dy equal to 0. So comparing this, we get m dash is equal to m into e raised to integration fx dx and n dash is equal to n into e raised to integration fx dx. Now we have to show this new equation 2 is exact. So for that, we have to find derivative of n, partial derivative of m dash with respect to y and partial derivative of n dash with respect to x. As m dash is equal to m into e raised to integration fx dx, here take partial derivative with respect to y on both sides. And so we get dA by m dash by dA by y is equal to dA by dA by y of m into e raised to integration fx dx. Now here, observe this second term, this is the function of x. As this is function of x, so this is the constant. So take this constant outside of that derivative, and so we get dA by m dash by dA by y is equal to e raised to integration fx dx outside dA by m by dA by y. Denote this is equation number 3. Now as n dash is equal to n into e raised to integration fx dx, take partial derivative with respect to x on both sides. So we get dA by n dash by dA by x is equal to dA by dA by x of n into e raised to integration fx dx. Here we observe that n as well as e raised to integration fx dx both contains x, both are functions of x. So we should use u into v formula here. And so dA by n dash by dA by x is equal to first derivative of u, that is derivative of n with respect to x, that is dA by n by dA by x, v as it is means e raised to integration fx dx as it is, plus u as it is means n as it is derivative of v with respect to x, that is dA by dA by x of e raised to integration fx dx. Now see this one, here we have to find derivative of e raised to integration fx dx. Derivative of e raised to integration fx dx is given by e raised to integration fx dx into derivative of integration of fx dx. And so we get dA by n dash by dA by x is equal to e raised to integration fx dx dA by n by dA by x as it is, plus this n also as it is, and derivative of e raised to integration fx dx is equal to e raised to integration fx dx into derivative of integration fx dx, that is dA by dA by x of integration of fx dx. Now observe that integration and derivative get cancelled, so here remaining only fx, and so we get dA by n dash by dA by x is equal to e raised to integration fx dx dA by n by dA by x plus n e raised to integration fx dx, and this is fx. Now see here both this term contains e raised to integration fx dx, so take e raised to fx dx as a common, and so we get dA by n dash by dA by x is equal to e raised to integration fx dx outside, inside we get dA by n by dA by x plus n into fx. Denote this as equation number 4. As you know, 1 upon n dA by m by dA by y minus dA by n by dA by x is a function of x alone, which is fx. Now transfer this n to that side, so we get dA by m by dA by y minus dA by n by dA by x is equal to n into fx. Now transfer this dA by n by dA by x to the right hand side, so we get dA by m by dA by y is equal to dA by n by dA by x plus n into fx. Means here we get value of dA by n by dA by x plus n fx as dA by m by dA by y. If you put this value in equation number 4, this equation 4 will become dA by n dash by dA by x is equal to e raised to integration fx dx dA by m by dA by y. Give that new equation as equation number 5. That equation 5 and equation 3 will be same. So continue in this way. Therefore, by equation 4 we have dA by n dash by dA by x is equal to e raised to integration fx dx dA by m by dA by y. This is equation number 5, and therefore by equation 3 and by equation 5 we have dA by m dash by dA by y is equal to dA by n dash by dA by x, and therefore new equation 2 is exact differential equation. First equation 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0 was not exact, but we multiply e raised to integration fx dx on both sides, we get second differential equation, which becomes now exact. As we multiply by e raised to integration fx dx, it is the integrating factor, and so we get if is equal to e raised to integration fx dx. And therefore, if 1 upon n dA by m by dA by y minus dA by n by dA by x is a function of x alone, say f of x, then e raised to integration fx dx is an integrating factor of the differential equation 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0. So this is the proof of that rule. This is the rule 3. Similarly, rule 4 is there. Now see, rule 4. If 1 upon m dA by n by dA by x minus dA by m by dA by y is a function of y alone, say f of y, then e raised to integration fy dy is an integrating factor of the differential equation 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0. Here instead of n, here is m, and these two terms are interchanged. Here dA by m by dA by y minus dA by n by dA by x, and here dA by n by dA by x minus dA by m by dA by y. Here is function of x alone, here is function of y alone. Here integrating factor is e raised to mx dx, here integrating factor is e raised to integration fy dy. So both rules are same. We can prove this rule 4 on the same lines as that of rule 3. Now we have to see examples on rule 3 and rule 4. So see the first example. Solve x square plus y square plus 2x into dx plus 2y into dy equal to 0. Solution. Given differential equation is x square plus y square plus 2x into dx plus 2y dy equal to 0. Denote this is equation number 1. You can write this equation as m dx plus n dy equal to 0. So we get m is equal to x square plus y square plus 2x, n is equal to 2y. Find out dA by m by dA by y and dA by n by dA by x. So dA by m by dA by y is equal to derivative of x square is 0, derivative of y square which is 2y, and derivative of 2x which is 0. So dA by m by dA by y is 2y. Similarly, dA by n by dA by x is 0 because this term doesn't contain x, means this is constant. So derivative of constant is 0. And here we observe that dA by m by dA by y not equal to dA by n by dA by x. And therefore, given differential equation 1 is not exact. As this differential equation is not exact, we have to make it exact. So for that, we have to find integrating factor. If you observe this differential equation is not homogeneous. As this is not homogeneous, so we cannot use rule 1. Similarly, observe this function x square plus y square plus 2x, which is not function of x into y. Means we cannot use rule 2 also. Now we have to see whether can we use rule 3. So for that, first find out dA by m by dA by y minus dA by n by dA by x. Value of dA by m by dA by y is 2y and dA by n by dA by x is 0. So this will become 2y minus 0, that is 2y. Now divide it by n. So we get 1 upon n dA by m by dA by y minus dA by n by dA by x is equal to 1 upon 2y into 2y. 2y get cancelled. This is 1. And we can treat this constant 1 as function of x. And therefore, 1 upon n dA by m by dA by y minus dA by n by dA by x is function of x. So we can use rule 3, and by using rule 3, e raised to integration fx dx is an integrating factor of the given differential equation. So we get if is this one. Now put here value of fx, which is 1. Integration of 1 with respect to x is x. So we get if is equal to e raised to x. Now multiply this integrating factor with the non-exact differential equation 1. We get e raised to x into x square plus y square plus 2x into dx plus 2 into e raised to x into y dy equal to 0. Denote this is equation number 2. So here new m and n are m is equal to e raised to x into the bracket x square plus y square plus 2x, and n is equal to 2 e raised to x into r. Take this e raised to x inside 1. So e raised to x x square plus e raised to x y square plus 2 e raised to x into x, and this n as it is. As we know, this differential equation 2 is obtained by multiplying integrating factor. So this differential equation 2 should be exact. As this differential equation is exact, its solution is given by integration m dx keeping y as a constant plus integration terms in n not containing x dy equal to c. Now here we have to put the values of m and n, and so we get integration value of m, which is e raised to x x square plus e raised to x into x square plus e raised to x into y square plus 2 e raised to x into x dx, y constant, plus integration terms in n not containing x. Here in n there is only one term, and that term contains x, so there is no term without x, so write down here 0 and this c as it is. Now we have to integrate this one, separate these three integrals here. So first integral will become integration e raised to x into x square dx. See second integration. In second integration, y is constant, so y square is constant. So take out this y square outside, so we get y square into integration e raised to x dx. And in third integral, 2 is constant, so take that 2 outside, integration x into e raised to x dx plus integration of 0 is 0 equal to c. Now see this integration. Here we have to use integration by parts. So use the LIATE rule. First function is exponential function and second function is algebraic function. So say this is the first function, algebraic means x square as first function and e raised to x is the second function. So use integration by parts. First function as it is, so x square as it is, integration of second function means integration of e raised to x, which is e raised to x, minus integration derivative of first function, so derivative of x square, which is 2x, and then integration of second function means integration of e raised to x, which is e raised to x dx, plus here this y square as it is, integration of e raised to x is e raised to x, plus this 2 as it is, x e raised to x as it is, equal to c. Take these 2 inside 1, and so x square e raised to x minus integration 2x e raised to x dx plus y square e raised to x plus these 2 inside 1, so we get integration 2x e raised to x dx equal to c. Now observe here, these 2 integrals are same. Their signs are opposite, but integrals are same. And so these 2 integrals get cancelled. One is positive, another is negative. So this and this integral get cancelled. So we get x square e raised to x plus y square e raised to x is equal to c. Now see this relation. This is relation between x, y and constant. So this is the general solution of the given differential equation 1. Hence the solution of that. Example. Now move to the next example. Solve x minus y square into dx plus 2xy dy equal to 0. Given differential equation is, write on that equation and give this is equation number 1. This is of the type 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0. So comparing, we get m is equal to x minus y square, n is equal to 2xy. Now find out dA by m by dA by y. Derivative of x with respect to y is 0, minus sign as it is, derivative of y square, which is 2y. So dA by f by dA by y is minus 2y, and dA by n by dA by x. Here y is constant, so 2x, 2y into 1 means it is 2r. Here we observe that dA by m by dA by y and dA by n by dA by x both are not same. Therefore, dA by m by dA by y not equal to dA by n by dA by x means given differential equation 1 is not exact. As this equation is not exact, we have to make it exact. Now observe this differential equation. This is not homogeneous, so we cannot use rule 1. See this first term, coefficient of dx, which is x minus y square, which is not function of x into y. So we cannot use rule 2 also. Now we have to check whether can we use rule 3. So for that you require dA by m by dA by y minus dA by n by dA by x. Here value of dA by m by dA by y, which is minus 2y, minus value of dA by n by dA by x, which is 2y. So we get minus 2y, which is minus 4y. Now divide this by n. So 1 upon n, dab m by dab y minus dab n by dab x is equal to, divide here by n, n means 2xy. So we get 1 upon 2xy into minus 4y. And so this is equal to that minus sign 2 upon x. Here this y get cancelled, 4 upon 2 it is 2. So this value is minus 2 upon x, and we observe that this is the function of x alone. So say this is fx. As 1 upon n dab m by dab y minus dab n by dab x is equal to f of x, means by rule 3, integrating factor is equal to e raised to integration fx dx. Now put value of fx, which is minus 2 by x, here, and so we get if is equal to e raised to integration minus 2 upon x dx. Take here minus 2 outside of that integral, and so we get if is equal to minus 2 outside integration 1 upon x dx. Integration of 1 upon x is log of x, so we get e raised to minus 2 into log of x. Now transfer this minus 2 to the power of x, so we get e raised to log of x raised to minus 2. Here e and log get cancelled, and so we get if is equal to x raised to minus 2. Transfer this x raised to minus 2 to the denominator, and so we get if is equal to 1 upon x square. As the integrating factor is 1 upon x square, now multiply this integrating factor with the given differential equation 1 on both sides. We get 1 upon x square into the bracket x minus y square dx plus 1 upon x square into 2xy dy equal to 0. Denote this is equation number 2. This is the new differential equation. This differential is equation obtained by multiplying integrating factor, means this should be exact. We can write this equation as 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0. So here new m and n are, m is equal to 1 upon x square, x minus y square, and n is equal to 1 upon x square into 2xy. Take this 1 upon x square inside 1. So we get x upon x square, that is 1 upon x, and then minus y square upon x square. And n is equal to, here we observe that 1 x get cancelled, so we get 2y upon x. So we get new m and n. As differential equation 2 is exact, its solution is given by integration m dx keeping y as the constant plus integration terms in n not containing x dy equal to c. Now put the values of m and n, and so we get integration value of m, which is 1 upon x minus y square upon x square dx, y as a constant, plus integration terms in n not containing x. N contains only one term, and that term contains x, so there is no term in n without x. So we get 0 dy equal to c. Now we have to evaluate this integral. Here integration of 0 is 0. Here y is constant, so you can take this y square outside. So here we get two integrals. In first integration we get integration 1 upon x dx, and in second integration minus y square outside. So we get minus y square integration 1 upon x square dx. So separate this integration, we get like this. As here y is constant, so y square is constant, take outside of that integral. Integration of 1 upon x is log of x, and integration of 1 upon x square is minus of 1 upon x, and so we get log of x minus y square into the bracket minus 1 upon x equal to c. And so log of x plus y square upon x equal to c. We observe that this relation between x, y, and constant. And so this is the general solution of the given differential equation 1. Now see one more example. Solve 3x square y raised to 4 plus 2xy dx plus 2x cube y cube minus x square dy equal to 0. Given differential equation is, write down that equation as it is and give this is equation number 1. This is of the type m dx plus n dy equal to 0. So we get m is equal to 3x square y raised to 4 plus 2xy, and n is equal to 2x cube y cube minus x square. Now take partial derivative with respect to y on both sides. So we get dab m by dab y is equal to, here this 3x square as it is, derivative of y raised to 4, which is 4y cube. So this term will become 12x square y cube. And then derivative of this with respect to y, 2x as it is, derivative of y with respect to y is 1, so it is 2x into 1, which is 2x. And so value of dab m by dab y is equal to 12x square y cube plus 2x. Similarly, we have to find partial derivative of n with respect to x, keeping y as a constant. So here y cube is constant, derivative of x cube is 3x square, so derivative of 2x cube y cube is 6x square y cube minus derivative of x square with respect to x is minus 2x. So we get values of dab m by dab y and dab n by dab x. We observe that both these values are not same. Means given differential equation 1 is not exact. So we have to make it exact first. So for that, we have to find integrating factor. But here we observe that this differential equation is not homogeneous. So we cannot use rule 1. Also, see the coefficient of dx, which is 3x square y raised to 4 plus 2xy. This is not function of x into y. Means we cannot use rule 2 also. Now we have to check whether can we use rule 3 or not. So for that, first we have to find dou m by dou y minus dou n by dou x. We already find these two values. So value of dou m by dou y, which is 12x square y cube plus 2x, then minus dou n by dou x, negative of this one, so it is minus of 6x square y cube plus 2x. Make this calculation. This 2x plus 2x, it is 4x. 12x square y cube minus 6x square y cube, it is 6x square y cube. Now divide it by n. If we divide it by n is 2x cube y cube minus x square. Now in numerator, take out 2x as a common. So we get 2x into 3xy cube plus 2. In denominator, take out x square as a common. So we get in bracket 2xy cube minus 1. Here 1x get cancelled. And so finally we get this is equal to 2 3xy cube plus 2 upon x into 2xy cube minus 1. Now observe this. This is the function of x as well as y. This is not function of x alone. Means we cannot use rule 3. Now we have to check whether can we use rule 4. So for that we have to find the value of dou n by dou x minus dou m by dou y. See this one, this value is this one, but you require dou n by dou x minus dou m by dou y. So take negative of this term, so which is minus 6x square y cube plus 4x. Now divide here by m, so we get minus 6x square y cube plus 4x upon m. M is 3x square y raised to 4 plus 2xy. Take out 2x outside in numerator and xy common in denominator. We get 2x 3xy cube plus 2 upon xy into the bracket 3xy cube plus 2. Now here we observe that x get cancelled and this round bracket 3xy cube plus 2 also get cancelled. And so this is equal to minus 2 upon y, which is function of y. As this is function of y, so we can use rule 4. So say this is f of y first. And therefore by rule 4, integrating factor is equal to e raised to integration fy dy. Now we have to put value of fy as minus 2 upon y here. And so integrating factor is equal to e raised to minus 2 upon y dy. Take out minus 2 outside of that integral. So if is equal to e raised to minus 2, 1 upon y, integration of 1 upon y, which is log of y. Now transfer this minus 2 to the power of y. So integrating factor is equal to e raised to log of y raised to minus 2. E and log get cancelled. So if is equal to y raised to minus 2. That is 1 upon y square. And so we get if as 1 upon y square. Now multiply this 1 upon y square if with the non-exact differential equation 1. We get 3x square y raised to 4 plus 2xy upon y square dx plus 2x cube y cube minus x square upon y square dy equal to 0. Denote this is differential equation 2. This is of the type 𝑀𝑑𝑥 plus 𝑁𝑑𝑦 equal to 0. So we get nu m as 3x square y raised to 4 plus 2xy upon y square and n as 2x cube y cube minus x square upon y square. Now separate here denominators. So we get 3x square y raised to 4 upon y square get cancelled. So we get 3x square y square plus 2xy upon y square, y get cancelled. So we get 2x upon y. Similarly here, 2x cube y cube upon y square, so we get 2x cube into y minus x square upon y square. We know this new differential equation 2 is obtained by multiplying integrating factor, so this equation, differential equation 2 should be exact. As it is, this equation 2 is exact, its solution is given by integration m dx keeping y as a constant plus terms in n not containing x dy equal to 0. Put values of m and n. Here value of m which we will find, which is 3x square y square plus 2x upon y dx. Here y constant plus terms in n not containing x. In n, there are two terms and both term contains x. So there is no term without x. So we should write here 0. And so we get integration over y, 3x square y square plus 2xy dx plus integration of 0 with respect to y equal to c. Now here we have to separate this integration. And so we get integration 3x square y square dx, y constant, plus integration of 2x upon y dx, y constant. Integration of 0 is 0 equal to c. As y is constant, so y square is constant. So take this 3y square outside of this integration and 2 upon y outside of this integration. So we get 3y square outside, integration of x square dx plus 2 upon y x integration x dx equal to c. Integration of x square is x cube upon 3. Integration of x is x square upon 2. Here 3 get cancelled, 2 get cancelled, and so we get x cube y square plus x square upon y equal to c. Multiply this whole equation by y, so we get x cube y cube plus x square is equal to cy. Now we observe that this is the relation between x, y and constant. So this is the general solution of the given differential equation 1. Dear friends, stay home, save lives, take care, and say bye-bye Corona. Thank you.